No. Oh. Huh? Okay. We've got everyone. We have less people than before. Okay, better. But still not the complete set.
No.
Okay, I can understand it. After I see that no one drops from the course, or after the day for dropping the course will be passed, I will start coming later too.
No, he didn't drop. He's a problem.
I'm trying to make a good impression and be a little more organized than usual.
Well, that's good.
So, anyone has urgent deadlines for the day? How long time do we have?
I have a class right after this.
Yeah, but what is the scheduled time for this class?
11 to 11.
Not 11.
12:30.
12:30?
To 1:45.
Okay. Should be sufficient. And I was supposed to go to be earlier, but it is not always possible. Who we are and what are we doing? Let's recall. What are we doing? So we are in the computational chemistry class, right? And we are progressing on more than three, several directions simultaneously. So we are trying to get some practical skills. We are trying to acquire some theories. And we are doing everything with hope to predict observables for experiment. Observables. Right? Make sense? I'm doing it just because it's more important to know where we go and how do we navigate. Because little pieces of information can always be picked up from books or whatever. It's better to be strategic first and then go through details. Which observables do we hope to get? So chemical stability. Whether the molecule will be realistic or not, will be stable or explosive. Electronic stuff like, I don't know, ionization potential, electron affinity, something related with redox of the specific molecule. Ionization, redox. What else? What can we predict? No, just give some ideas. If it is too hard, I will say no.
Transition energy.
Huh?
Transition energy. I mean absorption.
Transition energy. Okay, so different energies. Transition energy, binding energy. Transition.
Reaction pathway.
Yes, it will be a little later. What else? I have a little cheat sheet.
Absorbance.
Yes. And photoluminescence, right? So they're close. Reaction rate, or maybe distribution of products if there are more than one.
Molecular dynamics.
Yes, well, molecular dynamics is not an observable.
Yeah, it is.
It's a
No.
It's a method.
You can watch the
No.
the
Whatever you see on the screen of the computer is not observable, although you observe it. Observable is a property of real material.
NMR.
Okay. R, maybe EPR.
What's EPR?
It's the electron version.
What was it?
The electron version of NMR. So instead of looking at
Just replace nuclei to electron,
Yeah.
and then the same.
it's still magnetic.
Paramagnetic resonance. Ability to form charge transfer. Enough. Maybe there are more, but it's already a long list that we are tired to keep it in hands. Which theories? Well, we do Born-Oppenheimer separation of variables. Separation. So we put away electronic nuclear degrees of freedom. We will do force field, as everyone does for large pharmaceutical molecular dynamics. We'll do self-consistent Hartree focus. Self-consistent focus. Then the popular DFT. Then so-called TD, DFT. And if you have time, you'll do some expensive theories which are not helpful for big objects, like coupled clusters, configuration interaction. And the semester will end before we complete the whole list. So it is the wishes, it is theories, and which practical skills are we getting? Right now, we got 0 practical skills. We got just a bit of language of chatting with computer, so the Linux environment. Then we'll do building field to models. And then we'll do optimization. Optimization of geometry, electronic structure, excited states, and molecular dynamics. Molecular dynamics. And I'm already tired to draw this table. But if you focus on it more, we can find that some of the grid points merge together. So by doing like force field, one can do rough optimization. By doing Hartree Fox or DFT, one can do electronic structure. By doing so-called time-dependent density function, one can do excited states. And one can draw connections in this direction too. So when I will be in doubts what to tell, I will draw this table again and again, and we will discuss it as far as we progress toward the course. The handouts. Here is the evidence. Well, in case you will feel bored and abandoned on weekends, I can entertain you with a little homework, which you shouldn't take very seriously. It's more like a refresher, and it is not a key part of the course. First, I guarantee that everyone can make it 100%. And second, even if you are too busy that you skip it, you will not miss too much. Okay, so this was your weekend entertainment, which is really, it takes quicker to complete than to read. Do not worry. Now, who were Born-Oppenheimer? Why the streets are named after their names? If you are interested about streets named after Born-Oppenheimer, ask Levi. he should have an experience of driving the street this summer.
I did drive that street. I actually parked on it because I was lost when I first drove into Los Angeles.
Okay. It's just, it has even less relation to the course, because sometimes there is too many technical details and one can get an impression that what we do is completely deprived from real humans. But no, there are humans who do this and they get recognized. What else do I have for entertainment? Oh, I have a chapter from a book. So this is a book. I fairly do not know what Born and Oppenheimer were writing. Probably either something classified or boring, but I never read their writings. But there are a lot of books that try to repeat their idea after them, and what we do in class, in some sort, is repeating after those books. So this is a chapter summarizing what we were doing for last 3 meetings and what we will complete today. And the book is hard to find because it is printed in Germany, and the author is who? And the author of this book is Volkert May. And I'm aware of his book and his works because he was in my degree committee. So, and here's his biography. So we've got the homeworks, we got the biography of Born and Oppenheimer, and here is where we are on our course. So we are at the lecture number 5. We will complete Born-Oppenheimer approximation, and we will. This is the last time when we speak about ions and electrons together as one system. Later on, we will think about them separately. We will have enough background to believe that they have some connection. I do see a little. Well, there is no conflict. There is no problems. Everything is very, very nice working out. But on this pre-designed schedule, the student presentations are falling to next Thursday, which could be too early. So let's think whether one more lab will be sufficient to prepare these presentations. I do not see it as impossible, but on one hand, but on the other one, academic learning shouldn't be a stress for anyone. It should be completely pleasant and relaxed, on my opinion. So, again, review your opinions. Maybe if someone feels already that, oh, okay, I'm expert, I want to do this one, it will be possible. But if you are in the discomfort, we can shift and reorder the meetings. So 4 chapters. Good. I'm so happy to see you here. Please keep coming. But if by some reason you need to miss, most of what we are doing is pre-recorded before from previous years, and you can go to YouTube, see the content of the lecture, and add hits or whatever, just views to my YouTube channel. So today you do this one. And if you click one of them, it will have connections to others. So one can study at home. So here is what we had on the blackboard last time, when I decided that slides are not sufficient and one needs to scratch something on the board. So the idea is to practice the methodology of separating the variables. So if the Hamiltonian affects on different subspaces different parts of the system, like here it is x and y, then the wave function can be split onto a product. And our goal is to make rigorous transition of converting molecular Hamiltonian and molecular Schrödinger equation into two separate set of equations, one for electrons, another for nuclei. And this ridiculously simple homework is last time when you probably will practice building molecular Hamiltonian and looking on the terms. Just as a review of what we did before. Okay, so then we made up splitting of all terms in molecular Hamiltonians on part of the terms that are more related to nuclei and part of terms that are more related to electrons. And then we gave a benefit of the doubt to electrons and stolen one term which was in the gray zone, 2 electrons. So 3 for electrons, 2 for nuclei. And then this electronic Hamiltonian was diagonalized. Not in the computer, not on the paper, just in our heads. We assume that someone did diagonalize it for us. And if someone did diagonalize this Hamiltonian, then we have a good set of functions, of eigenstates, and they are used to compose the solution of the bigger equation with unknown coefficients. And those unknown coefficients do depend on positions of ions. And our task for last meeting and for today is finally to get an equation for these unknown coefficients, which also can be interpreted as nuclear wave functions. Objections? Questions? Shouldn't be, because there were no objections last time. So it is a slide that was last time on the slides, and it has terms of overall molecular Hamiltonian, where everything that did relate to electrons is summarized in the third line. So from electrons we have electronic Hamiltonian and electronic eigenvalues. And the rest comes from the overall molecular Schrödinger equation. It does explicitly have only nuclear operators, but the function, unknown function, is cast in form of expansion over the electronic wave functions, green stuff. Since our goal, there is nothing new, I'm just reviewing what was last time. Since our goal is to get an equation for, I don't know again how to pronounce it, chi, chi, this symbol. We want to find this symbol. And chi sub a, chi sub a, he sub a. We want to get rid of phi, well, phi, this letter. And in order to get rid of it, we want to apply orthogonality relation. So we want to take phi with different index, phi with our present index, integrate and get either 0 or 1 and remove them. So that finally we will get equation only for this chi sub a. And where we stopped is that we need to establish close connection between yellow and green parts, but they have red parts between them. So the product of red times green must be swapped, if it is possible. And it is indeed possible in all terms except the first one, because there is some quantum nature in these operators and these functions. So we want to swap red and green very, very carefully. Good. And it is what Born and Oppenheimer were doing, and what why people name streets after them, because they were swapping green and red. Well, in our notation, not the traffic light, green and red. So, and this is what we had on the blackboard before we left the room. So it is first, second, third, and fourth lines. And the only problematic is line number 1, where we have kinetic energy operator of nucleus, and here product of nuclear wave function chi and electronic wave function phi. We have fear. No, we don't have fear. We have care for swapping operators and eigenfunctions in their order, because operators may change their functions. So we are going to look on this T capital, chi, and phi, and see how they can be swapped, how they can be processed. So this T capital, okay, wake up. Review has completed. Now we are going to look at the new material. So now there will be something a little bit more new compared to what we had last time. So this rectangular brackets do replace capital T sub n. And it does have the derivative over positions of ions, d over dr. And last time we agreed that d over dr is operator of momentum, right? d over dr is operator of momentum, and if you have momentum squared, then it will be second derivative over the position. Should I cover it a little bit more once again, or it is okay? That momentum is derivative over position. Okay? Good. Give me secret sign or write an email if you object this statement. I will be very happy to argue. So we do have second derivative and two functions. When I was making this course of lectures last time, there was an opportunity to draw by finger on a screen, and it is what I was doing. So now I just will use this. It's also touch screen. Maybe there is a way to draw something.
There you go.
Okay, it is a pointer. But other annotations.
Oh.
Uh-oh.
There's the pen instead of a laser pointer.
Okay. Oh, it doesn't want to make annotations in the PowerPoint and then save them. It needs probably a little different software, but everything is already written here. And it is so simple that you can do it yourself. It's equivalent to first 2 weeks of calculus. Here's my pointer. Very good, very good. So here's function 1, here's function 2, here's apostrophe 1 for one derivative, apostrophe 2 for second derivative. So when we do first derivative, is derivative applies to first function, second unchanged. Derivative applied to second function, first function unchanged. And then we have a second derivative. When we keep practicing this first term and apply derivative once again, we have a second derivative applied to first function, second function changed, first derivative applied to both functions. And then when we deal with the next term, we got it split onto two terms again. First derivative of each function and second derivative of the last one. Good. And this was our first term in the molecular Hamiltonian. And here is the same stuff. What is this? No, it is not what I wanted to do. Okay, and here is the same operation, just written in this calligraphic partial derivative symbol. So two terms are equivalent when each of the functions is taken for the first time. So we can put factor 2 in front and remove this one. And then we do have second derivative of electronic function and second derivative of the nuclear wave function. Stop me if you feel discomfort. I do not have a goal to lose a track or that everyone feels uncomfortable.
But question.
Please.
In the Born-Oppenheimer approximation, you're saying that the ions are fixed, correct? And the electrons move instantaneously.
The electrons are instantaneously rearranged to follow any change in position of ions.
I only ask because a lot of these terms would die if you considered it at fixed position.
That's right. But if we are at finite temperature, then ions are moving and kinetic energy is non-zero. Okay, so do we have any emotional attachments to any of the terms in this last line? Any of them looks most ugly and any of them look most pretty? So let me share the private opinion. If you do have nuclear wave function, this chi sub a, and we apply nuclear kinetic energy operator, d over dr nuclear, then it will be mostly authentic kinetic energy. Nuclear kinetic energy operator applied to nuclear wave function. More like classical, traditional, standard type of kinetic energy. And many people call it pure kinetic energy term. So this one is a good term, and the rest is subject to be considered as a garbage. Or something, well, maybe not garbage, but something exotic that is not for simple guys, but for boring stuff which is very exotic and rare. So Born and Oppenheimer decided, okay, let's keep the terms that we can understand and remove the terms that we cannot, and see what happens. So they kept this last term, and they just told, when you do not want to do something, you do not tell that it is my laziness. You tell, it is my approximation. It is my approximation that treating this term is not necessary. I'm going to provide justification later. So it is how science is done. So when this approximation is legitimate and possible, or when it is not legitimate. So if the just boring to look on the screen all the time. If the ions are moving really quick, then the other terms can be important. And when ions moving quick in our life, in our chemical labs, like
High temperature?
yes, or if you have explosion in the lab, which we probably do not try to avoid, right? Combustion, explosion, high temperature. What else? High intensity laser radiation, plasma, stars, core of sun, nuclear explosion, and maybe processes around it. So something exotic. Maybe lightning, chemistry of lightning. But if we do ambient temperatures or like liquid nitrogen temperatures, solids, quantum dots, molecules, not synthesis, not glow discharge, but actual materials, then kinetic energy of nucleus is so slow itself, and these exotic terms are even smaller, then it is safe to avoid these exotic terms. We need to get back to them if we are at high temperature first, and if the temperature is not high, if we passionately need connection between electronic and nuclear degrees of freedom. Like if we are looking for non-radiative recombination, which takes very long on a typical time scale of process, not picoseconds, nanoseconds. So it's really slow process. But if we really need this number to see how quickly the photoexcitation recombines, then one may look back on these terms. But for most of the properties of materials, one can neglect it and live a happy life. Make sense? Okay, so we put a bold red crossing lines on the terms that mix electronic and nuclear degrees of freedom. So we keep only the pure kinetic energy. And we may want to it's not the following saying doesn't apply too much to natural sciences. It is more to biology. But if someone was interested in reading scriptures, then one can make notice what was the first task to Adam. The practical task, what to do. To give names to animals, if you look. And it is one of the things that intermediate level, well, like science of the maybe 70s, 80s centuries, the biology was keeping to do. So not looking on the logical connections, but simply giving naming. We are going to neglect these strange terms, but we are going to give it a name. So because it is a coupling between electronic and nuclear degrees of freedom, and because it is on the such high temperature that adjustment of electrons does not follow change of ionic positions, this means it is not adiabatic. Like if electrons adjust quickly, it is adiabatic. If they do not have time to adjust, it is non-adiabatic. So these two terms will be referred to as non-adiabatic coupling. And here are the expressions for them. If we are not yet late in time, I can practice and reproduce
Are you missing a 2?
I can miss a 2 all the time.
Oh.
The 2 should be in front of the first term, yes. Let's camera control. 1. Okay. Since there are too many sums and looking on the pre-recorded equations is very important. I wouldn't remember anything. So let me practice my memory and do. So we give it the name theta just to follow the good chapter that you already have. And this is your chance to use the second opinion. If I lie, Volcker May doesn't have it. So there are derivative over position to nuclear wave function. There is an electronic wave function, derivative of electronic wave function in respect to nuclear wave function. And here we do have an average over electronic degrees of freedom. And according to Levi, there could be a factor 2. So, taking derivatives over ionic position of nuclear wave functions is a natural thing. There is nothing surprising. But taking the nuclear derivative over of electronic wave function is something exotic, right? And here we have first derivative. So it is first order non-adiabatic coupling. And if one keeps ionic wave function untouched and one has t, then it will be second derivative in respect to nuclear wave functions to the electronic wave function. And it is a second order non-adiabatic coupling. Typically, second order is even smaller. And we told that 99.9 computational chemists neglect non-adiabatic couplings at all. And 99.9999 neglect the last term. So even those who deal with non-adiabatic couplings, they focus only on the first term. And if you are belonging in this range of scientists who do non-adiabatic coupling, and reviewer tells you, I cannot accept your paper, your coupling is not precise. You tell, okay, what is the reason of discrepancy? Well, we have neglected second order, maybe it is a reason. You provide some justification for discrepancy, which you always should think about. And if you looked on the equations there were a couple of summation signs. So if one wants to be very precise, there are so many ions. And often one also, if one looks on the transition from any possible electronic state A to a fixed state B, one also often adds summation over electronic indices. This was a peak in of most complicated part of our course. If you didn't panic now, then you will not panic for the rest of the course. Yes, please.
What is adiabatic coupling and what is non-adiabatic coupling?
I do not know what is adiabatic coupling. I never seen this expression. This is an excellent question. I will try to think and find something. But it is, I see the logic of how you build this question, but fairly.
Would it be like the exchange?
It could be purely electronic processes, but I do not want to lie. I better postpone the answer. Thank you. So, there were no panic signs by now, which is good. The rest will be simpler. It doesn't mean that we have completed the course, but this was the largest intellectual challenge. If you accept this statement, the rest is more like protocols that one should repeat. Okay. If we drop this non-adiabatic term, the rest of terms do have electronic wave functions in the form of convolution, bra times cat, or like star times wave function without star, and it will be equal according to Dirac Kronecker symbol. It will be either 0 or 1. So it gives us chance to remove electronic wave functions from the consideration. So first term is split onto two subterms. First one is the pure kinetic energy acting on nuclear wave function, and the rest of electronic wave functions is erased due to orthogonality. The non-adiabatic cannot be treated this way, but we drop it completely. We just tell it is our approximation for low temperatures. Low temperatures doesn't mean helium or liquid nitrogen. It means they're less than 5,000 Kelvin. Something like this. Reasonable temperatures. And then for the nuclear kinetic energy, you have the same delta function. For electronic eigenenergies, same functions, and for total eigenenergies, same function. Another stuff that we always had a summation over all electronic wave functions with sum sub A, right? Because our original wave function was presented as and now we do have expressions that looks like summation over A, delta AB, something, chi A. When we do have summation and Kronecker delta, they symbolically cancel each other. It's like sigma eats delta, right? And in everything what is remaining in this term, we replace A to B. We keep only one index and we remove Kronecker delta and summation sign. Okay. This slide is not needed. But if we remove this summation sign, we do not have any electronic wave functions, and we have only ionic wave functions with chi sub B. And you see it here and there. And we do not need to make them as several levels, because now it is a simple equation. So here is the first term, here is the second, third, and the fourth. So we do have an equation for nuclear wave function, chi sub b. So it is a Schrödinger equation for nuclear wave function. What is good and what is bad, and what is specific of this function, of this equation. So first, as any Schrödinger equation, it will have many solutions. So there will be several solutions for nuclear wave function. And maybe if we are not going to Raman spectroscopy, we are interested only in the ground state solution. But formally, many solutions. Second observation is that we do have potential of nucleus repelling each other, right? But in addition, we do have a term that is contributed due to electrons. So due to interaction between electrons and ions. And the summation of nuclear repulsion and the electronic energy that parametrically depends on positions of nucleus play a role of potential energy in Schrödinger equation. So typically, this is operator of energy, and it should have kinetic part and potential part. And our potential is contributed by two terms. First term is just electrostatic repulsion of nucleus, and the second one is eigenenergy of appropriate electronic state. So there is an imprint of electronic state onto nuclear motion. I don't know if one can call it adiabatic coupling, but there is a connection. And one can call it with another letter, U of R. And since it is potential energy, and since there are so many ions, so it will be multi-dimensional potential energy, one can add the word surface. Or this abbreviation PES. Okay, so what is potential energy surface? Do we have any brief definition? Any ideas? I can try to write it down, but we need to discuss and get. So it is something that plays a role of potential energy for nucleus, but it does depend on quantum states of electronic system.
So if you keep the same electronic state and vary the nuclei, you can see how the energy of that state differs.
Keep the same electronic state and change nuclear position. Explore profile of not total energy, of potential energy. Potential energy. I like it because it is correct, but I do not like it because it is long. But I do not have the better solution. Can we try to verbalize it even like something that one can memorize and answer quickly? Just reformulate potential energy of nucleus for specific electronic state. Is it the same? Potential energy of nuclei for specific electronic state. Okay, so this is most important take-home message of all this consideration. You will probably keep some traces of memory about Born-Oppenheimer approximation, but it is not of immediate practical importance. But definition of potential energy surface, the concept of potential energy surface, is what we will be dealing with for a long time from now on, at least for like 3-4 meetings. Is it a question? So the nucleus feel the electronic state, depend on which electronic state we are. And if we do have electronic system in like ground, excited, second excited, the potential that nucleus experience will be different. Immediate application, immediate connection is photoreactions. When you photoexcite, and reaction goes on. What was not possible in ground state becomes available in excited state. Very good. I think we are getting success. There is a pre-recorded images of these possible potential energy surfaces. So if it is interatomic
Switch.
yes, thank you. This is important. Good. Now I see why you were looking with a little question in your eyes on me, because I was happy looking at my screen and you didn't see what I'm observing. So here's oversimplified example of different potential energy surfaces. If we have this internuclear forces, electrostatic forces, plus contribution of electronic energy for ground state, B equals 0, then it will be one surface with one equilibrium point. But as far as we go to first excited, we do have different equilibrium position, different curvature, and if you go to higher excited states, it may show something exotic. I'm not claiming that there will be 3 minima, but it would be something different. So if we do accept the concept of potential energy surfaces, then we open the door to so-called force field methods. I will return to this idea a few statements later. We are almost happy. We were able to make a legitimate approximation for treating electronic and nuclear degrees of freedom separately. This is a very important leap forward for the main task of computational chemistry, to solve Schrödinger equation for systems with huge amount of degrees of freedom. Now we reduce number of degrees of freedom at least twice. Electronic, nuclear. Next step, do we want to solve this Schrödinger equation for nuclear degrees of freedom all the time? We do not. Why?
Costly.
It's costly, but we should look good in eyes of reviewers and give some more respectful background.
The only time that it's very important to do it is when the non-adiabatic coupling increase, so you jump states.
Well, if we have very light ions and very high curvature, like maybe CH bond, it may show some quantization. But if we look back onto quantum theory course, then you may recall. You do not need to recall it. We are fine without any memory from previous life. But if you did attend any of quantum courses, you have seen the quantum classical correspondence principle. If one makes wave packets for nuclear wave packets for nuclear degrees of freedom, and looks at them as Gaussian wave packets with higher probability to find ions at that position and lower at other one, this Gaussian wave packets have width. And this width of the distribution of probability to find nuclei somewhere strongly depend on mass and Planck constant, and it is important only for small light objects on a short time scale. If we look for Gaussian wave packet of projector or computer mouse, you will find that uncertainty, the width of the distribution, will be very, very small. And even if you look not on electrons but on nuclei, then the uncertainty of to find the nuclei in a certain place in space is also very small. And due to this quantum to classical correspondence, it is a very good approximation to believe that position of ions is very certain. Uncertainty is small, meaning the solution of... I do not want to be boring and I want to show pictures rather than saying. Camera. Okay, there is a little spot. I'm stealing pens from myself. So if you do have this potential energy surfaces, and this is nuclear degrees of freedom, then here is how the solutions for this chi sub b will look. Right? And it will have the certain uncertainty. But since the mass of ions is high enough compared to electron, this uncertainty can be assumed negligibly. So it is another approximation. It is not always correct, but still we can predict a lot of properties of true molecules with this approximation. So we assume that this width is small. And if this width is small, we can stop caring about the width and the shape of wave packet. Instead, we will speak only of the central expectation value of center of such wave function. So we care of x, y, computation value of nuclear wave function. Position of nuclear wave function. So center of wave vector. Center. And we will call it just R sub I, position of ions. So we are advanced enough, we went through rigorous procedure of separating electronic and nuclear degrees of freedom, but now as an approximation, we start to believe that ions are classical particles with certain positions. CPA, classical path approximation. And these classical particles experience potential energy surface, which is yet different for different electronic states. So it's classical particles moving in different potential depending on which electronic state we have. Very good. Good. So you see here classical limit point charges. We are close. We are close to completion of this chapter of this subject. Another reference, review point about general quantum theory, which could be new or can be very, you can be very acquainted of it. So how many brands, how many shapes, how many different types of Schrödinger equation do you know? Is this the only Schrödinger equation? Let me show you.
Isn't there as many Schrödinger equations as there are Hamiltonians?
Well, this is correct. This is trivial, but other, in principle, different types, different classes of Schrödinger equation. Give me some ideas. See, the one that we were drawing here is time independent, when we just find eigenstates and eigenvalues. But generally, this is the limiting case. The more general Schrödinger equation has also dependence on time, because wave function is propagating, evolving forward in time. And here is the Schrödinger equation for nuclear wave function, and this nuclear wave function depending on time. So actually what we want to do, we want to merge together our classical path approximation, our limit of very narrow wave packet, and an idea that nuclei obey time-dependent Schrödinger equation. So if we fuse together these two ideas, then instead of equations for propagating these nuclear wave packets in time, we will have only equations for propagating in time of central point of the wave packet. So it will be equations which are very, very similar to Newtonian equation of motion from classical mechanics. Stop me. Raise hands, object if you do not like this idea. No one objects. Either everyone is very happy or everyone stopped following a long time ago. Well, I'm just projecting on myself sitting in class. The most natural thing is read news and from time to time, well, worse of it can be playing card games between each other. So, track the center of the distribution in the same spirit as one does for classical mechanics. I feel it is time to stop now or maybe in a few minutes, because humans cannot concentrate for a long time, even if we are assigned to stay longer.
I have a little bit confusion.
Huh?
What is the center of wave function you say?
You can go to the blackboard and write a question yourself.
No, I mean.
No, you can. I will be very surprised if you cannot. I can dictate you if you have doubts.
What I need to write wave function?
You need to wait until I focus camera on you. Okay. Which board are you going? Okay, here, yes. So, suppose that you have wave function chi of r capital, and then you want to find expectation value of position. For r. Yeah. So I can dictate you, but you can do it yourself. So angular brackets, open angular bracket, r capital, close angular bracket, equals, integral, dr capital, chi of r, chi star of r,
And
of r, times r,
But you gotta.
and you need to have r between them, or somewhere here. Multiply by r.
yeah. Yeah.
Does it answer your question?
But I mean, what is you said center means average suppose.
Expectation value.
Okay.
Yeah, thank you.
Nah, that's a wave function. It's just continuous thing. Then what is the center of it?
But if your wave function describes, let's say, 10 nuclei, you just find the center of your wave function.
Because of the quick dephasing for all, because when we do have a lot of nuclear degrees of freedom, we do have a quick dephasing, and even complicated shapes converge to single maximum Gaussian wave functions very quickly. If you do not perturb your system by light or external sources of energy, it will come naturally to Gaussian shape. So it is very good approximation. A little thing that is highlighted as Born-Oppenheimer approximation in many short textbooks. In many textbooks, one skips all the equations that we did, and they write only this equation that I'm focusing at. So, molecular wave function that depends on electronic and nuclear degrees of freedom rigorously is expanded as a summation of electronic wave functions with expansion coefficients as a summation over all basis states. But in case of Born-Oppenheimer approximation, this summation is replaced by a product, just one electronic function by one nuclear wave function. And in the chapter from the book that I have distributed, Born-Oppenheimer separation is split onto 10 pages. In most of the books, it is like half page, and only this equation. So if instead of summation, we can just product. If total wave function equals product of electronic times nuclear, many people call it just Born-Oppenheimer approximation. So the electronic and nuclear degrees of freedom are separable. They can be represented just as a product. Here is electronic part and nuclear part. What do we have? Potential energy surface that is composed of electrostatic repulsion and contribution from electronic energy, and that's it. I think it is sufficient. Let me see, I was leaving some other slides, but they are not part of the lecture. They are more like entertainment. So probably when we meet on Tuesday, you will fill up this form that you have seen on our web. And what else? Spin is what you already know. Login is what you know. And we are going to learn graphical connection and practicing Gauss U. That some of you are already exposed to the software, but it is some standard popular software that is very helpful. So it is our goal for the lab on coming Wednesday. Okay. Number 2, instructor's table. At this point, I would like to announce completion of lecture number 5. Meeting is dismissed. Okay, I will stay here if you have some questions, but you are free to go. And you were free to go before 2.